the scoreboard's layout, we have decided to have two sets of LED matrices, 8 LEDs tall and 19 LEDs wide for displaying the team names, and two sets of three 7-segment displays for displaying the score, and two sets of two 7-segment displays for displaying the stats of the match like wickets and etc., and a set of 6 7-segment displays for displaying the time during the match. We have conducted a few surveys to decide the size of the characters displayed. So for good visibility at a distance of 100 meters, we have found out that 7 inches is the right size, considering 100 meters is the approximate length diagonally of a football field. To decide on the maximum brightness required by the display, we conducted a few surveys. We found out that 25,000 lumens per meter square is the maximum brightness required on a summer midday for the human eye to recognize the text over the bright sunlight. The design of the LED matrix display. We have chose to have LEDs in parallel connected across rows and columns in the LED matrix. We have chosen a 7x5 display for displaying each character. We are driving each LED with a transmission gate driver so that it has a very good digital low and digital high and can supply the current required. It also has very fast switching rates. Since the LEDs are connected in parallel across the rows and columns, an LED can be switched on by giving a digital logic high to one side and digital logic low to the other side. This can be ensured by connecting the transmission gates with the rows to voltage low, that is ground, and connecting the transmission gates of the columns to VCC. We have implemented the whole LED matrix on a PCB. We have soldered it and it looks as follows. We use a diffuser for better visibility, and we have implemented switching cycles for a range of alphabets A, B, C, D and E. We require a 12-bit bus for driving the LED matrix for one character. This is very unfeasible if we increase the size of the matrix. So we have implemented a serial interface for driving the whole circuit, which is scalable, so that even if we have a larger display matrix, we can just increase the size of the registers or thing. The serial interface is a 12-bit register with serial input and parallel output. The parallel output is connected to the transmission gates, and the serial input and clock are connected to the microcontroller, where the data for each stage is given serially by the microcontroller to the registers. You can observe the fast switching states for displaying the letter D in the video. This video has been slowed down 32 times compared to normal time for visibility of each state. The 7-segment display. Each segment in the 7-segment display is a set of 4 LEDs connected in series with a MOSFET acting as a pull-down switch. The MOSFETs used for pull-down are NMOS transistors. All the segments have a common voltage source which powers them up. Here is an image of the soldered 7-segment display and the connections. The ICs visible are the MOSFETs that drive the 7-segment displays, and the 7-segment display is soldered onto a PCB. Here is an image of the 7-segment display soldered onto a 0 PCB displaying the number 2. Here the 7-segment display is cycling through 3 numbers 0, 2 and 3. Each segment of the 7-segment display is lit individually and is directly interfaced to the microcontroller. Rest of the numbers have not been implemented, but their mappings have been recorded on paper. Since the LEDs are driven by MOSFETs with very high current ratings of the orders of tens of amperes, to increase the required light output, we can just replace the LEDs with high power LEDs and increase the supply voltage to get very high brightness as output.